So it's lecture number 15. And we are going to discuss magnons. So let me briefly remind you what we discussed before regarding local theory of magnetism. So we started with a system of non-interacting spins subject to magnetic field. So there are some spins. And we have found that the susceptibility of this system, chi node, behaves as 1 over temperature. Then we allowed spins talk to each other, and adopting molecular field theory, we discovered that chi actually is a constant divided by T minus some critical temperature Tc, below which ordered state is formed, which means that for ferromagnetic situation, and we begin with discussion of ferromagnet, the ground state of this system, namely at temperature equal to 0, is corresponding to parallel alignment of all modes. So this is a ground state, temperature equal to 0, although from the phenomenology we cannot draw any conclusion about ground state. We said that there is a critical temperature, and below this critical temperature the isotropy existing in our system at high temperatures is normally describing system correctly. Namely, we have a spontaneous symmetry breaking, and this spontaneous symmetry breaking assumes that there is certain direction along which spins are magnetized. So everything is consistent with the second order phase transition theory. So we said that magnetization appears at critical temperature, and then by constructing very simple Brillouin-Langevin theory, we were able to describe the order parameter which is the magnetization, which then leads to conclusion that at 0 temperature we have ground state corresponding to net magnetization taken maximum value, so all spins are aligned parallel to some given direction. So the question which we are going to discuss today is, first of all, what happens with excitations in this system. So what are the excitations? We know the ground state. We derive the law of excitation, namely dispersion of excitation, energy dependence of the wave vector. This will be maybe 2/3 of the lecture. And in the remaining part, we discuss what happens if we have several sublattices. If you have a possibility to have, for example, 2 different sublattices, this is the most simple case for bipartite lattice. So what then changes and what are the excitations in this system? So in order to do it, we first need to start with some microscopic model. And the simplest possible microscopic model, as I said, we are discussing spins as 3-component operators. It has components in X and Y and Z, contrast to Heisenberg model, which you discussed before. So the simplest possible model is so-called Heisenberg model, and I will start with isotropic version, again anticipating any questions. Which assumes that, first of all, we have a lattice. In all previous considerations, the lattice was not that important, so the treatment which I discussed with you is equally applicable for so-called glassy system where there is no translational invariancy. However, from this very moment, I will assume that there is a regular lattice of spins. So we are talking about atoms whose inner shell is not completely filled. So the atoms provide local moments, and these local moments talk to each other with very simple interaction. So it's sum over n, sum over n not equal to n, g and m, s, n, s. So, which means that spin in the lattice, on the lattice side corresponding to vector Rn, which I'll denote as n, is talking to spin sitting on the position m, and this is Rn. For most of what I'm going to discuss today, I will assume that this interaction is short range, namely only nearest spins talk to each other, and on the last lecture, namely Friday, we will see how this model actually can be justified and actually derived from Hubbard model, which assumes tight banding approximation, so small overlap, and therefore small hopping of electrons sitting on different sides in the presence of very strong on-site Coulomb interaction. So we will see how to justify this model, and since I'm going to discuss ferromagnetic state, which means that the ground state corresponding to parallel alignment of spin, from this point of view, the exchange integrals g and m should be positive. In this case, indeed, parallel alignment means that this will be just s squared, and there is a minus sign. It corresponds to lowest possible energy. Okay? So, any questions so far regarding the model? In principle, if I have a magnetic field, then G mu bar H sum over I S sum over N S and Z. But for what I'm going to do now, I will assume a situation when magnetic field is 0. So this term doesn't play any important role. Okay. In this exchange, let us write separately exchange in xy plane and exchange in z direction. So this is minus sum over n, sum over m not equal to n, g and m. I assume isotropy. This is sxn sxm plus syn sym plus smz smz, and I will assume that this is transverse part. Transverse because the quantization exists in which sz spin operator is diagonal is z, and therefore everything which is perpendicular to the quantization axis corresponding to diagonal form of operators is transverse. And this is longitudinal. And for practical purposes, it's very convenient to introduce operators s plus minus n, which is s x n plus minus I s and y. So these are raising and lowering operator. You can easily construct from Pauli matrices the operators S plus and minus, and you will see that S plus has elements above diagonal, S minus has elements below diagonals, and and therefore Sx is S plus plus S minus over 2, and S and Y is S plus minus S minus over 2I. That transverse part, S and X, S M X plus S and Y, S M Y can be written down. I plug it in 1/4 S n plus plus S n minus times S m plus plus S m minus because I have I S n plus minus S n minus S m plus minus S m minus. So this is a transverse part. If I open brackets, I have 1/4. You see that terms containing two creation or two S plus or two S minus operators are gone because I have a minus in front of the second term. Therefore, what remains is S n plus S m minus plus S n minus S m plus, and I have two terms, two similar terms, therefore I have factor of 2, and this is 1/2. So this term is then 1/2 S n plus S m minus plus S n minus S m plus. Okay? So let me now adopt Fourier transform for this Hamiltonian. Again, I will do calculations for ferromagnetic case in all details, but for the second part of the lecture, I will give you some sketch. Okay, the rules for Fourier transform. I need to define it because I would like to define Fourier transform differently for plus and minus with a different sign in the exponent in order to avoid having Q minus Q connections. So S plus minus n is equal to 1 over square root of n sum over Q, S plus minus Q e to the power plus minus I Q Rn. I define Fourier transform symmetric, putting 1 over square root of n to be able to define inverse Fourier transform. Plus minus is 1 over square root of n sum over n S plus minus n e to the power minus plus I Q R. Okay? Good. Let's now recall that there are commutation relations. So spin operators on the same side commute as S plus and S minus. Let's say M is first of all delta and M and 2 times SZ. So these are commutational relations. So if we take a Fourier transform now, this is S n plus S m minus minus S m minus S n plus is equal to delta n m 2 times S and Z. Let me write down Fourier transform of the right hand side and left hand side. What we have 1 over n sum over Q1, Q2, S plus Q1, S minus Q2, minus S minus Q2, S plus Q1, times exponent I Q1 Rn minus I Q2 Rm. This is what we have in left hand side. In the right hand side, this is 2 delta Nm sum over Q S Z Q e to the power 1 over square root of n I Q R. Okay? So if we see the left hand side of this equation, I would probably do something else. Sorry. So what I did, I multiplied by exponent and integrated and summation over Q1 and Q2. So I will do the same with the right hand side. So this is 1 over n, 2, sum over Q1, Q2, S n Z, I Q1 Rn minus I Q2 Rm. This is actually identical to what I did, delta n. So if we then, if we now look at this commutational relations, what we see inside the brackets, S plus Q1, S minus Q2, minus S minus Q1, S plus Q2, Q2, Q1. At zero temperature, as I said, all S Z are aligned in a long certain direction. So at zero temperature, we can say that all S and Z are equal to S. Right? Then we take it out of the bracket, and what we have here is delta function Q1, Q2. Because n is anyway equal to m, this is the same radius vector, but the summation over Q will give me delta function Q1, Q2. Therefore, I'm saying that without losing generality, I can say that this commutator is some constant times delta symbol Q1, Q2. If temperature is not equal to 0, and as I said, I'm interested to discuss the ground state, 0 temperature, and very low temperatures in the vicinity of the origin. So, as I said, if temperature equal to 0, this is S. If temperature is not equal to 0, the right hand side is proportional to S, Z, and average. But what is very important to conclude after this exercise is that S plus and S minus operators behave very much like bosonic operators. So therefore, I can say I can introduce new operators. I can say that S plus Q is 1 over square root over 2S times operator AQ, and S minus Q is 1 over square root over 2S operator AQ dagger. And therefore, what I have here, that commutator AQ1 A dagger U2, I will have 2S, which was in front of the right hand side. You remember that Sn plus Sm minus is equal to 2S n Z delta n m. So this commutator is just delta Q1. At temperature equal to 0, it is exact. At final temperature, there are small deviations from as long as the temperature is. Of course, what I'm going to do, and you will see it almost immediately, is considering large spin, namely the situation when spin S is much larger than 1. And what we will do is sort of the 1 over S expansion. So then we will do this in a few minutes. One can immediately see that the transverse term, when we introduce new bosonic variables, will be just A dagger plus A dagger A. So what we need to express now is ZZ term, namely the longitudinal one. And let's recall that our spin algebra assumes that there are two diagonal elements. Namely, we construct bases of Pauli matrices such a way that Z operator, the operator acting in Z direction, is diagonal, but operator S square is also diagonal and has eigenvalues equal to S plus 1. So Sn square for each and every side is equal to S times S plus 1, and it is equal to Snx square plus Sny square plus Snz square. What I'm going to do, I'm going to express Snz in terms of Snx and Sny, assuming that this conserving quantity does exist. Okay, how I do that? Of course, this is also 1/2 Sn plus Sn minus plus Sn minus Sn plus. This is what I did before, and I will apply Fourier transform. Therefore, this is 1/2 sum over Q1, Q2, S plus Q1, S minus Q2, minus plus S minus Q2, S plus Q1, times exponent I Q1 minus Q2 Rn. And therefore, this is, well, 1/2n. We don't forget about normalization factor, plus Snz square. I don't need this Fourier transform anymore. I will continue there. So S times S plus 1 is equal to S n z square plus 1 over 2n. When I introduce my new bosonic variables, I have normalizing factor square root over 2s. Therefore, this is 2s. And here I have sum over q1, q2. A q1, A dagger q2 plus A dagger q2, A q1, and exponent I q1 minus q2 Rn. So from the commutation relations, I have A dagger is equal to A dagger A plus delta function. So this term is then A dagger q2 A q1 plus delta function q1 q2. These terms are the same, and what I have is S n z square is equal to S times S plus 1 minus term with delta function times exponent will give me n after summation, and therefore I have term S. This is what originates from the delta function, and the remaining is S over n sum over q1 q2 A dagger q2 A q1 e to the power I q1 minus q2 Rn. So this is S square plus S. Therefore, I can write down that S n z is a square root over 1, so S square minus S over n sum over q1 q2 A dagger q2 A q1 e to the power I q1 minus q2 R. If I take S square out of the bracket, this is S times square root 1 minus 1 over S n, and there is this sum. Now, if S is much larger than 1, I can expand my square root. So this is a reason for this quasi-classical description of spin. In quasi-classical way, spins are replaced by bosons which are harmonic oscillators. Therefore, if I do this expansion, and you remember that square root 1 minus x is equal to 1 minus x half, I keep only lowest possible terms, I will get that S n z is equal to S minus 1 over 2n sum over q1 q2 A dagger q2 A q1 e to the power I q1 minus q2 Rn. Okay? So now I can plug in everything there and write down the transverse and longitudinal terms separately and then combine them. Okay, is it clear what I'm doing, how I introduce bosons and why bosons is good approximation in the limit of large spin? transverse term, H perpendicular, is minus sum over n, sum over m not equal to n. I have s plus and minus, s minus, s plus, but in the second term, since n is not equal to m, first of all I can commute them and I can rename n and m. So those who prefer at all steps keep Hamiltonian in Hermitian form can keep doing it, but what I will do now, I will write G n m s minus n s plus m. Okay? As I said, I took this term, relabel n and m, and commute. And I use the fact that n is not equal to m. So self-action is excluded. So if I take a Fourier, this is minus 1 over n. Each has a square root. Sum over n. Sum over m not equal to n. Sum over q1, q2. G and m. A dagger q1, a q2. And there is exponent I q1 rn minus I q2 rn. And there is a factor 2s coming from normalization. Okay, now the exchange integral. Of course, the first observation which we do is that the interaction between spins sitting on n and m side should depend only on the distance between these spins. Therefore, G and m actually depends on modulus n minus m. It's quite reasonable, right? And as I said, for almost all what I'm going to do, I will confine myself by considering interaction between nearest neighbors only. So in this summation, therefore, it is quite convenient to introduce new variable, n minus m is equal to L, and therefore n is equal to m plus L. This is what I'm going to plug in here. Rn is equal to Rm plus L. And I will replace this is by GL. And I will take summation over M and L. So with this exponent, I have now I Q1 minus Q2 Rm. Plus I Q1 L. And taking summation over M, since nothing depends on M, sum over M e to the power I Q1 minus Q2 Rm gives me n times delta function Q1, Q2. Factor of n is cancelled out, so what then remains? Remains summation over L, G which depends on L, and summation over Q. This is minus 2s to s. Summation over Q, a dagger Q, a Q, e to the power I Q L. So now we can introduce this quantity, namely sum over L, where L assumes that we are dealing with certain neighbors, in particular nearest neighbors, sum over L, G, L, I, Q, L. If I am in the nearest neighbor approximation, nearest neighbor means that for your lattice only nearest neighbor talk with a strings J. So this is then J sum over L e to the power I Q L. And if I introduce the number of nearest neighbors Z, so this is then G Z times some function gamma Q. So Z is a number of nearest neighbors, and gamma Q is 1 over Z sum over L e to the power I Q. So then this term is minus, let me see that I didn't not make any mistake. Minus 2s z j sum over q gamma q a dagger q a q. So this is what I wanted to write down. So let me recapitulate it some way here, that h perpendicular is minus 2s z j sum over q gamma q a dagger q a q. Okay, so in order to have you a clear picture what is factor gamma is, let's compute it assuming that you have a simple cubic lattice. Okay? For simple cubic lattice, so if we take this side, so we have then z equal to 6, right? Simple cubic. Z equal to 6. We have 6 nearest neighbors. 1, 2, 3, 4, 5, 6. Okay? And we need to take a summation over L which takes value ax plus minus x, ax plus minus x, ay plus minus y, plus minus ay, and plus minus az. Since the lattice is cubic, so all lattice constants in x, y, and z directions are the same. So gamma q for simple cubic lattice is 1/6, and when we take summation over ax, so we have iqx a plus minus iqx a plus iqy a plus minus iqy a plus iqz a plus minus iqz a. So therefore this is 1/3 cosine QXA plus cosine QYA plus cosine QZA. So this is how function gamma Q looks like for simple cubic lattice. In particular, the interesting case, what happens if we have a very small q. Namely, we are in a long wave limit and q is much smaller than inverse lattice constant. So A is lattice constant here. So this is A. So if q times A much smaller than 1, we can expand cosine. So we have 3 times 1 1/3 is 1 minus actually 1/6 q square A square. So this is expansion for small q. So in your homework you have some problem corresponding to interaction or exchange contest beyond nearest neighbors. For simple cubic lattice, next to nearest neighbors will be, for example, this one, this one, this one, this one. So you can compute the number. Maybe someone knows this by heart. The very same way, one can take a summation over next to nearest neighbor, next and next, so increase the radius of coordination sphere. But what is important here, that this is Z. In some sense, the molecular field theory, which we are going to discuss Friday, is not only expansion with respect to large S, it also assumes that you have a large coordination number. Just don't forget about that. So now, after we did this exercise, which is very important, let's now deal with the longitudinal term. Okay, H parallel. So this is H perpendicular and this is H parallel. Is equal to minus sum over n, sum over m not equal to n, G and M, S and Z, S and Z. For this sake, I will now substitute this S and Z and write it down as sum over n, sum over m not equal to n, G and M, and this is S minus 1 over 2n sum over q1, q2, a dagger, q2, a, q1, e to the power I, q1 minus q2, rn, times s minus 1 over 2n, sum over q3, q4, a dagger, q4, a, q3, e to the power I, q3 minus q4 rn. Again, let me be sure that I did not make. Actually I did some mistake. I don't know why you didn't tell me that. Because when I replaced SZ term, I had a factor 2s. And therefore, this 2s, 2 cancels this 2. So in the square root, so please correct it. So what I'm saying is that after replacing, so the there is factor 1 over n and factor 1 over n here. Please go back to this expression and correct. So this 2 is actually, I forgot to cancel. Otherwise I will come to contradiction. So, you see that in this product I have 3 sorts of terms. First term is constant, which is minus s squared times sum over n, which will give me n, sum over m will give me z, and I have a j for nearest neighbors. So this is the main term, which is the ground state energy. And then I have 2 terms quadratic with respect to A. And they scale with S, because each of these terms will be proportional to S. And then I have a term when I have 4 operators A, and this term doesn't contain S. Since I'm in the limit of large spin, I will keep leading term, and I will keep the term proportional to S. So this is then plus 1 over n, sum over m not equal to n, g n m, a dagger, sorry, sum over q1 q2, a dagger q2 a q1, I q1 minus q2 Rn. So, what is important that there is a sign plus. Then, what do I have here? I will take summation over n. Summation over n will give me delta function q1 equal to q2 times n. So n will be cancelled out. I will continue writing it here. H parallel is equal to this energy I will denote as E naught plus 1 over n times n times sum over L GL times sum over Q A dagger Q AQ. Sum over L GL is equal to Z times G. So this is, and of course times S. There is S sitting here. So therefore this is E naught plus J times S times Z well, sum over L, GL. Once again, something is, of course, I have 2 terms like that, and therefore there is a factor of 2. As I said, I consider this times this plus this times that, therefore there is a factor of 2. Good. 2s, and I have sum over Q, A dagger Q, AQ. So, now I'm in a position to combine everything. So, H parallel plus H perpendicular so my H is equal to E naught, and E naught is this one, plus sum over Q, plus this constant, 2s Zj sum over q. I have 1 minus gamma q, a vector q, aq. So, what I did is writing down the Hamiltonian of excitations. I introduced new variables which corresponds to plus, minus, raising and lowering operator. I told you and explained why these operators are almost bosons. At least they are bosons in large spin limit. And therefore, I can map my Heisenberg Hamiltonian, this is Heisenberg model, to the system of oscillators, harmonic oscillators, which don't talk to each other. Therefore, I diagonalize my Hamiltonian and I present it in terms of low-lying excitations. And these low-lying excitations, these bosons, are magnons. Okay. So, what do these magnon mean? In other words, these magnons are called spin waves. And what are the spin waves in the ferromagnets? So at any finite temperature, your spin precesses a little bit along some direction. And this precession of the spins, which can be transferred from spin to spin, is precisely spin wave. But since, let's now look at the dispersion. I said epsilon q, the dispersion of magnons, is 1 minus gamma q. Gamma q is defined here. This is 1 minus 1 over z, sum over L, I, u, L. We have seen that for small q, gamma q at q much smaller than 1 over a is 1 minus 1, 6 q square, a square. So therefore, times this constant times 2 times s j z. Therefore, at small q, my dispersion epsilon q is lambda q square, where lambda is equal to 2s j z, this is z, times a square. Keep it 6 here. So, the point is that magnons are excitations which are characterized by dispersion epsilon q, which is quadratic with respect to the wave vector. So in the sense, if we are back to our discussion of Bose-Einstein condensation, so magnons are quasi-particles which mimic ideal non-interacting Bose gas. So the dispersion is like q square over 2m. Here we have a stiffness which depends on spin, which depends on j, which depends on the number of nearest neighbors. However, the dispersion of magnons is proportional to q square. Therefore, by knowing that, you can find all thermodynamic properties. So magnons in ferromagnets behave like harmonic oscillators. You can compute energy, you can compute specific heat, you can compute magnetization. I will leave this problem for you. I'm not going to discuss thermodynamics in this very moment, because in the remaining half an hour I would prefer to discuss with you what happens if this interaction constant exchange integral is negative for nearest numbers. I find it more important. But what is important here? Let's compute. So, as I said, this is a dispersion. The distribution function NQ average is both the distribution function EQ over temperature minus 1. But if we compute the number of magnons, we compute the number of magnons. Which is sum over Q and Q average, which is integral in d-dimensional space. This will be Q to the power d minus 1 dq. For long wave excitations, for small q, and you know, in all problems and all divergences in condensed metaphysics are related with a long wave limit, namely small q. For small q, I expand the exponent. So this is then temperature lambda q squared. And you see that this integral is t integral q to the power d minus 3 dq. So in dimension 3, this integral is regular and doesn't have any divergence. In dimension d equal to 2, the integral diverges as dq over q, which means it's temperature times logarithm size of a system over lattice constant. So divergence at small q is regularized by inverse size of the system. This is the smallest possible q. At large q, the integral is regularized by one of the lattice spacing. This is highest possible energy. So you see that in two-dimensional case, we already have a problem that number of magnons diverges. And this is nothing but the Mermin-Wagner theorem, which Professor Nersessian told you. So the long-range order in a two-dimensional system is only possible if temperature equal to 0. In one-dimensional case, it will diverge as the size of system. So even temperature equal to 0 that cannot help in regularizing this integral. So you see that for a low-dimensional system, we do have problem with excitations, and this is related to the fact that in low-dimensional system, actually fluctuations are so strong that they destroy the long range. Okay. Any questions so far? So we started with the lattice model. We introduced bosonic representation for spins, which describes spin in terms of harmonic oscillators. And this representation is pretty good for large spin. And by doing that and ignoring, so what kind of terms we ignored? We ignored terms which A dagger A. This is interaction among magnons. One can take it into account. And actually this interaction term, like we did it with boson-Stein condensation and weakly interacting gas, is very important for determining the inverse lifetime of the excitations. If you do that, namely you take into account magnon-magnon interaction, A dagger A, you compute the inverse lifetime, you will find out that while the energy scales as a q square for small q, the inverse lifetime scales as q to the 4 power. Therefore, magnons in three-dimensional, this is q to the 4, are well-defined excitations because the inverse lifetime is much smaller compared to characteristic energy. And magnons are also well-defined excitations in the limit of small q, in the long wave limit. Okay? Good.
Since this is a discrete system, there should be finite monetization even if the temperature is not 0, right?
Of course. This is, we are dealing. And in principle, by using magnons, one can well describe this area. From the point of view of thermodynamics, you have Hamiltonian magnons, you can compute magnetization you can find that magnetization is temperature to the power 3/2. Yeah. All these thermodynamical computations can be done with this Hamiltonian, which describes the physics at low temperatures, so close to the ground state. Okay, let me change gear. And sketch what happens if the interaction between spins is negative. So now we are discussing antiferromagnetic case. Again, Friday I will show you how to characterize this system in the vicinity critical temperature approaching from above. So this is the subject of Friday lecture, and how to come to the description of critical phenomena. Antiferromagnet. So if we are talking about exchange integral on nearest neighbors, I will assume that G and M are negative for nearest neighbors. What does it mean? If this exchange integral is negative, then this scalar product should correspond to antiparallel alignment, because then we gain additional sign minus, and this will lead to the lowest possible energy of the system. So this antiparallel alignment is called antiferromagnet, to be contrasted with parallel alignment, which is a ferromagnet. However, the crucial point here, that in principle one can view this antiferromagnetic state. Suppose we are dealing with the ground state. First of all, we should deal with so-called bipartite lattice, which allows us to color our lattice in two colors, red and blue, up and down, and we can view this bipartite lattice as sublattice A and sublattice B, which are embedded one into another. So for sublattice A, we have all spins up. For sublattice B, we have all spins down. So this is a bipartite lattice. Not all lattices allow such color. For example, if we have triangular lattice, so suppose this is up, suppose this is down, so these are nearest neighbors. So this is elementary cell. So then, what should we put here? This is so-called frustration lattice, frustrated. It is not compatible with antiferromagnetic state. It is not bipartite, while the square lattice or simple cubic lattice is compatible with coloring. Hexagonal lattice is also compatible. One can see that hexagonal lattice is also bipartite lattice. One can put up, down, up, down, up, down, and no problem with that. But please remember that not all lattices are compatible with antiferromagnetic state. Now, let me sketch how one can treat this antiferromagnetic system. Okay? The Hamiltonian is the same, but the exchange integrals are negative. So therefore, on two sublattices, I will introduce two colors of bosons. Namely, on sublattice A, I will write that Sn minus is square root over 2s over n, sum over q, A dagger q, I q r n, and Sn plus would be square root over 2s n sum over q a q e to the power I minus I q r n. But on a sublattice B, I should introduce another set of bosons. I will call them B. So this is S minus M is square root over 2S over N sum over Q. B dagger Q, I Q R M, and S plus M square root over 2S over N sum over Q, B Q e to the power minus I Q R M. So we have two colors. And then I do pretty the same. With longitudinal tone, I will then have G parallel, which will be something, I should assume that spins or moments on sublattice A and sublattice B are in the opposite direction. But for H perpendicular, I will have something A dagger A plus B dagger B, because it originates from squaring from this. However, for H perpendicular, namely this term, H perpendicular, I will get terms which are A dagger B, because this is interaction of S plus on the sublattice A with S minus on sublattice B. A dagger B plus B dagger A. One can do what I did before and elaborate the coefficients. I will leave this problem to you. If you do everything correctly, you will get, after plugging in, that your Hamiltonian is E node tilde, another constant, plus S times Z times modulus J, H is equal to E node plus S times modulus G times Z, and here we have sum over Q, A dagger Q AQ plus B dagger Q BQ plus gamma Q A dagger Q BQ plus B dagger Q AQ. So this is what you will get instead the Hamiltonian for ferromagnets, assuming that there are two sublattices. So you see that in contrast to ferromagnets, where we have only one sublattice, this Hamiltonian, although being quadratic with respect to U harmonic oscillators, so A and B are bosons, this Hamiltonian is nevertheless not yet diagonal. And what we need to do is to diagonalize this Hamiltonian, introducing linear combinations of A and B as new variables. So we need to diagonalize this quadratic form the very same way as we did it for the Bose-gas. So it means that we need to come to Bogoliubov transformation. Namely, we are saying that AQ is UQ, or U alpha Q minus V beta Q, and BQ is minus V alpha Q plus U beta Q. These are the linear combination, and we need to find coefficients U and V such a way that in new variables, which is supposed to be bosonic, the Hamiltonian is diagonal. Requiring that the alpha and beta fields or states are bosonic, we will immediately get a condition that U square minus V square is equal to 1, which is determinant U. So this is equal to 1. This is condition number 1. The condition number 2 can be obtained from the condition I plug in my variables old variables and express them in terms of new variables, I will write down my Hamiltonian in terms of alpha and beta, and I request that the off-diagonal term alpha dagger beta plus beta dagger alpha is equal to 0. It will give me a second condition, the very same way as we did. If you perform that, and I'm not going to do it for the third time, I did it for bosons, I did variational procedure for superconductors, which is very similar spirit. For control, I will write you down the equations. So the equations are 4 times, so first of all, EQ, the new dispersion, which is in front of the diagonal form, is equal to, we denote this is A. Let me denote this is coefficient, but let's call C, you know. So C times U square plus V square plus 2UV gamma. And the coefficient, the equation for U is 4 times U square minus 1 is equal to gamma Q square 1 minus 2 times U square. So you recognize that this was 2 times UV equal to gamma U square plus V square. This side minus, but so then if I solve this equation, it defines me coefficient U and coefficient V. I'm not going to proceed with this. I only write it down that the dispersion relations epsilon Q is equal to SZ modulus J square root 1 minus gamma Q square. So please do this exercise. I think after we did it 2 times, you can do it yourself. So let's look at these dispersion relations. So we have seen that gamma Q is equal to 1 minus Q square A square over 6 for small q and simple cubic lattice. Simple cubic lattice is a bipartite lattice. So gamma Q square for small q is 1 minus Q square A square over 3. And if we plug it in here, we will find out that epsilon Q, AQ, is SZ modulus J, 1 over square root of 3 times A times Q. In the limit Q, A much smaller than 1. So what you see that for antiferromagnets, the magnons are characterized by linear dispersion relation. The very same way as it happens for weakly non-ideal Bose gas. This is why I'm always emphasizing this similarity. For ferromagnets, we don't need to diagonalize Hamiltonian. It's already diagonalized in terms of the oscillators. For antiferromagnets, because of existence of 2 bipartite lattices, we need to do that. But when we did, we found that antiferromagnetic magnons are sound-like. So namely, they are characterized by linear dispersion. Therefore, the universality class for the lowest lying excitations in the antiferromagnets is the same as in weakly interacting Bose gas. So, and moreover, the thermodynamics of the magnons are the same as the thermodynamics associated with acoustic phonos. So this is sound velocity. So you can immediately draw all possible conclusions of the contribution of magnums into thermodynamics, seeing the similarities with the phonos. Several important comments. Again, like in ferromagnetic case, when we do have at the transition point spontaneous symmetry breaking, and this spontaneous symmetry breaking is associated with the breaking of rotational symmetry. So below critical temperature, as we see for antiferromagnet or for ferromagnets, the rotational symmetry is broken and spin can only rotate on a small part of a sphere, while above TC, spin can freely rotate in all possible directions. So this is the symmetry which is broken. Rotational symmetry, or symmetry of rotation on a sphere, is continuous symmetry. As a result of continuous breaking of continuous symmetry, in accordance with the Goldstone theorem, we have a gapless excitations. So these gapless excitations for ferromagnets are characterized by quadratic dispersion. These gapless excitations for antiferromagnets are characterized by linear dispersion. These magnons in both cases are Goldstone, namely gapless modes. What is the order parameter in the antiferromagnets then? In the ferromagnets we saw that the order parameter is uniform magnetization. So the net magnetization of the system at zero temperature corresponds to alignment of spins. In the antiferromagnetic situation, we have two sublattices, and in each of them spins are aligned either up or down, but net magnetization, which is sum of magnetization of sublattice A and sublattice B, is equal to 0. There is no net magnetization. M is not order parameter. But the difference of magnetizations on sublattice A and sublattice B is then playing the same role as uniform magnetization for ferromagnets. Therefore, this difference of two magnetizations, which people refer as a staggered magnetization, namely number of spins on sublattice A minus magnetization associated with spins on the sublattice B, is the order parameter. Therefore, instead of M, we will call it N. We discuss more about this on Friday. However, the ferromagnetic case corresponds to instability in the uniform situation. Therefore, it is instability associated with the smallest possible wave vector. For the antiferromagnet, existence of two sublattices already means that you have certain vector, reciprocal vector in Q space, and the instability associated with the difference of two sublattice magnetization is corresponding to the instability on the reciprocal vector. So this is not the instability of Q equal to 0. Then, with the linear dispersion, you introduce, you do thermodynamics with the help of the Bose distribution function. Again, NQ average is 1 over EQ over temperature minus 1. For sound-like excitations, it's 1 over Q. And you can have impression that the number of magnum would not diverge in two-dimensional case, because the integral will be Q dq over Q, not Q squared, and does not logarithmically diverge. This is, of course, true, but it is not in the contradiction with Mermin-Wagner theorem. In principle, what you should do correctly, both in ferromagnets and antiferromagnets, you should refer to spin-spin correlation function. And as you will see, and we discuss it again on Friday to summarize everything, this spin-spin correlation function will demonstrate some divergence in two-dimensional case, both in ferromagnets and antiferromagnets, and it's related to the fact that the instability for antiferromagnets is associated with a finite wave vector. So there is no contradiction with the Mermin-Wagner theorem, and this antiferromagnetic order is equally impossible in two-dimensional structure everywhere except temperature equal to 0. However, Yet another comment is that for ferromagnets, if J is positive, you can introduce net magnetization, which will be sum over n SMZ, and you may see that this to be order parameter commutes with the Hamiltonian. So the magnetization is conserved. It commutes with the Hamiltonian. However, so the ferromagnet is therefore true ground state. You can do also the exercise, introduce staggered magnetization, namely the difference of magnetization in two sublattices, and you may see that this operator doesn't commute with the Hamiltonian. It creates great debates of whether antiferromagnetic is a ground state or not ground state. The situation for today is it is proven mathematically that in 2 and 3 dimension and highest dimension, antiferromagnetic state is indeed the ground state of the problem. The alternative to antiferromagnetic states are so-called spin liquid states, which are highly debated in the high temperature superconductivity. We will see it on the slides on Friday. That's probably all. Any questions? The last probably thing, since I mentioned this spin-spin distribution functions, spin-spin correlation function, we have two sorts of spin correlation function, SZ Q omega, SZ Q omega, and S plus Q omega, S minus Q omega. This I would refer as chi ZZ, SQ omega, and this is chi plus minus Q omega. So, below TC, let's first consider ferromagnets. Below TC, when you have broken the symmetry, rotational symmetry, so Z is your particular direction, so your spin cannot go into the, cannot cross equator. It oscillates either on this part of hemisphere or on that part of hemisphere, here. Therefore, the Z correlation function, ZZ, is gapped. However, the plus minus correlation function, which corresponds to this precession of the spin, as we have seen in the dynamics, it corresponds to magnons, so it has poles omega square minus lambda q square square, and there is lambda q square. Let me write omega plus I delta. So, as you see, the poles of the transverse correlation function do in fact describe the excitations, namely magnons, in your system. If we are talking about antiferromagnets, then we need to talk about Q close to the reciprocal vector. Then, in fact, these spin wave excitations with linear dispersion appear in the vicinity of reciprocal vector. Nothing happens with uniform state, namely Q is equal to 0, it's not critical. So you will have omega square minus C square Q square, but you will have a constant in the numerator, because you are dealing not with 0 Q. And here it's certain conservation law, by the way. Therefore, the Fourier transform of this magnetization for ferro and antiferromagnet will diverge. This is what I was saying. So, but again, the longitudinal susceptibility is gapped, while the transverse one describes the excitations, namely the real part of the pole. So poles of the response functions are characterizing excitations. So the real part is responsible for the dispersion, while the imaginary part is responsible for the inverse lifetime of the excitation. And for antiferromagnets, the same way as ferromagnets, one can prove that in the long wave limit, namely for Q small, which deviates a little bit from the reciprocal vector, the lifetime, inverse lifetime of the excitations is much smaller compared to the energy of the excitation. So magnons are well defined quasi-prime.